Okay, it is November 15th, 2020. This is for Physics 350 Sacramento City College. And this is the worksheet number 6, I think it is, for the class. Okay, so this is handed out to the class, and then here are the solutions. All right, so number 1 in your own, semi-trailer trucks have an odometer on one hub of a trailer wheel. The hub is weighted so that it does not rotate, but it contains gears to count the number of wheel revolutions. It then calculates the distance traveled. Okay, so a lot of that isn't that important to the problem. The fact of the matter is, if the wheel has a 1.15 meter diameter and goes through 200,000 rotations, how many kilometers should the odometer read? How far should the truck have gone had the wheel gone through 200,000 rotations if it has a radius of 1.15 meters? All right, now, first thing we do is we convert from rotations to radians. And the second thing we do is we're assuming there is no slippage. So, in other words, whatever arc length along the wheel surface we travel, that's the same distance that the truck travels linearly. Okay, if there's no slippage, that's true. So, we convert the 200,000 rotations right here into radians. Okay, that's what it would work out to be. That many radians. Here it's 2 pi radians per 1 revolution. So we know that the change in angle equals the change in arc length over r. Therefore, the change in arc length, which is the amount of surface of wheel, okay, the amount of surface of the wheel that we cover, okay, how much surface goes around, is equal to the change in the angle times the radius. Okay, the angle is going to be, the change in angle is going to be 1.257 times 10 to the 6 radians. All right, that's the amount of radians we would go through if those tires went through 200,000 rotations as the truck went down the road. Now remember, this is diameter up here. Okay, this is the diameter. You got to watch for stuff like this. So we have to cut that in half, and half of 1.15 meters, which is the radius, which is what we need here. It's going to be 0.575 meters. Multiply it out. We get 7.226 times 10 to the 5th meters. That means our arc length overall would have been 723 kilometers. That's how many, that's the length, or the arc length of the circle that went around. Okay, that's the amount of tire surface length that went around. So that means that's how far the truck went. The truck went 723 kilometers. What is the period of rotation of the Earth in seconds? What is its angular velocity of Earth? And given that the Earth has a radius of 6.4 times 10 to the 6 meters at its equator, what is the linear velocity on Earth's surface? Well, 24 hours is 86,400 seconds. You can go 24 hours. For every 1 hour, there are 3,600 seconds. Okay, and you get 86,400 seconds. Okay, now the angular velocity, that's going to be this guy here. Okay, it undergoes one complete revolution every 24 hours. Okay, so that is one complete revolution every 86,400 seconds. That second got a little bit away from the 86,400, but that's S goes with this guy. It's not S equals, it's all this equals this. So one revolution, going back up here, one revolution is 2 pi radians. 2 times 3.14 is going to be 6.28. So that's where the 6.28 comes from here, okay? That's 2 times pi. And they dropped the seconds here, but anyway, we've got that many radians and that many seconds. We go through 7.3 times 10 to the minus 5 radians per second. That's the rotation of the Earth in seconds. Every second that goes by, we go through 7.3 times 10 to the minus 5 radians. Okay, the velocity, okay, the linear velocity is going to be equal to the angular velocity times the radius. Okay, we were already told that the radius up here was 6.4 times 10 to the 6 meters times the angular velocity, which we found up here. So we get 740 meters per second. So, as seen from the sun, we are traveling 740 meters every second that goes by, as seen from the sun. Close to 5 football fields every second that goes by. Okay. A truck with 0.420 meter radius tires travels at 32.0 meters per second. What is the angular velocity of the rotating tires in radians per second? What is this in revolutions per minute? Okay, so angular velocity, once again, you go the linear velocity, which we're told was 32.0 meters per second. Okay, divided by the radius, which we're told right here is 0.420, so it's just V over R, and we get 76.2 radians per second. So we go through 76.2 radians every 1 second that goes by. That's what the truck wheel is doing, the tires are doing. Now, if we want it for revolutions per minute, well, we go back the other way. We've got 76.2 radians per second. There are 2 pi radians per 1 revolution. So when you do this, you've got revolutions per second. But we want revolutions per minute, so we have to get rid of the seconds. And so the seconds are on the bottom here. We put 60 seconds on the top. There's 60 seconds in 1 minute. We get 728 revolutions per minute. I don't know what that is right there. That's a mistake right there. That's not supposed to be seconds right there. That's supposed to be minute. We got minutes here. Okay. So that's not supposed to be S. That's supposed to be M. This is right. This is 728 revolutions per minute. Okay. Olympics ice skaters are able to spin at about 5 revolutions per second. 5 complete revolutions, 5 complete 360-degree rotations every 1 second that goes by. What is their angular velocity in radians per second? Well, angular velocity, that's the omega. It's 5 revolutions per second. You go through 2 pi radians every 1 revolution, so they're going through 31.4 radians per second. That's how much of an angle they're going through per second, 31.4 radians. Be 5 complete revolutions, 5 times 360 degrees. Okay. What is the centripetal acceleration of the skater's nose if it is 0.12 meters from the axis of rotation? So they're telling you the radius right there. Okay. So the angular acceleration, we've got this equation right here. It's one of the equations we have. It's r omega squared. Okay, r is the 0.12 meters up here, from up here. Okay, and then we just figured out what the angular velocity was in radians per second. We got to square that. Don't forget to square it. 118 meters per second squared. That is the angular acceleration of the tip of their nose. An exceptional skater named Dick Button was able to spin much faster in the 1950s than anyone since. I should look him up. I wonder if he's still alive. At about 9 revolutions per second. So not 5 revolutions per second like up here, 9 revolutions per second. What was the centripetal acceleration of the tip of his nose, assuming it is at 0.12 meters from the central axis of rotation? Okay, so we start out, there's our radius. Now we have 9 revolutions per second, so they just skip this step right here. So they have the 2 pi radians per 1 revolution. That'll give us radians per second. That'll be the angular velocity. We square it times by the radius. 384 meters per second squared. That'd be his angular acceleration compared to the 118 meters per second squared if I get just a normal skater. Then it says, comment on the magnitudes of the accelerations found. It is reputed that Button ruptured small blood vessels during his spins. Well, what they want you to do is take this acceleration and divide it by the acceleration due to gravity. So if you go 384 meters per second squared, divide by 9.8 meters per second squared, is around 12. 12 times larger than the acceleration due to gravity. This is quite a lot of acceleration in itself. The centripetal acceleration felt by Burton's nose was 39.2 times larger than the acceleration due to gravity. No, it is no wonder that he ruptured small blood vessels in his spins. Okay, a rotating space station is said to create artificial gravity, a loosely defined term used to for an acceleration that would crudely be similar to gravity. Crudely similar to gravity. I don't know. I've never seen these in the United States, but I've seen a couple of foreign films, like from France or someplace like that. These people go into this spinning thing. It spins really, really fast, and it's spinning so fast it can actually climb up on top of it, be off the ground, and they're just spinning around, 5 feet off the ground. Okay, so it almost seems like you could almost kneel on it or even stand on it. And that's kind of what the idea here is. You're spinning around so fast that that basically it's kind of odd. It's kind of like, well, I don't. Let's get on with this. Anyway, so the outer wall of the rotating space station would become a floor for the astronauts, and the centripetal acceleration supplied by the floor would allow astronauts to exercise and maintain muscle and bone strength. It would feel like you're on the surface of the Earth. That's the whole idea. There's been books, science fiction books, written about these sorts of things up in space and the people trying to live on them. So that might be something that comes, who knows, maybe in your lifetime. All right, so more naturally than the non rotating space environments. If the space station is 200 meters in diameter, so 100 meters in radius, right? 200 meters in diameter, so that'd be 2 football fields across about. What angular velocity would produce an artificial gravity of about 9.8 meters per second squared at the rim? Well, the angular acceleration, again, is the radius times the angular velocity squared. But now what we want for our centripetal acceleration is g, 9.8 meters per second squared. So we solve g, or we solve for the angular velocity in terms of g. So that's going to be equal to the square root, because the angular velocity is squared. Square root of g, the 9.8 meters per second squared, divided by 100 meters, because the diameter is 200 meters. We want 100 meters. So we have to spin that thing at 0.313 radians per second. Okay, so then once you get it up there and you start spinning it, there's nothing to slow it down. So you would just keep spinning at that rate forever and ever and ever via Newton's laws of motion. Calculate the centripetal. This is number 24 in your own now. Calculate the centripetal force on the end of a 100-meter radius wind turbine blade that is rotating at 0.5 revolutions per second. Assume the mass is 4 kilograms. What do we know about centripetal force? It's equal to the mass times the centripetal acceleration. Okay, so we use the angular velocity squared. Where's my mouse at? We use why does it disappear? There it is. We use the angular velocity squared. We use this equation right here. The radius we were given up here, it is the radius, not the diameter. So you've got the 0.5 revolutions per second. Okay, remember we want that in radians per second. And then the 6.28 is just 2 pi. So it's 2 pi radians per second, but 2 pi is 3.14, double it is 6.28. That's all that is. They're just converting from revolutions per second to radians per second. That's all that is. Square it, multiply by 100. 4 times this squared times this. And you get 3.9 times 10 to the third newtons. So that would be the centripetal force acting on that wind turbine blade. Remember, that's the force in towards the center of rotation. All right, I told you we're going to do anything. See, this has a banked curve, so see this? All right, I put it up here in case you're interested in, but I'm going to avoid banked problems, okay? Because we'd have to spend more time on it. I want to get going ahead. We're behind where we're supposed to be. Okay, number 33 in your own. Calculate the Earth's mass given the acceleration due to gravity at the North Pole is 9.830 meters per second squared, and the radius of the Earth at the pole is 6,371 kilometers. Remember that the radius from the center of the Earth to the poles is a little bit less than the radius from the center of the Earth to the equator, because the Earth is a little bit flat. Its spin, its rotation causes it to flatten out a little bit. All right, so basically, um, you've got the acceleration due to gravity at the surface of the Earth. This comes from, you remember that mass times acceleration, little m, which is an object we would stick there. Little m times the acceleration would be equal to basically. Let's see, do I have it available easily? Yeah, there it is right there. So instead of Fg, we put little m, that little tiny mass, times g. That little tiny mass is like m1. M2 is like the mass of the Earth. So those two masses go away. We're left with little, just g by itself equals big G, the universal gravitational constant, times the mass of the Earth divided by the distance from the center of the Earth to the surface of the Earth. Okay. Let me go back and look again. All right, so that's what we have right here. So the mass of the Earth would be equal to the radius of the Earth at the pole squared. That's the number right here. Okay. Times the acceleration due to gravity. It's a 9.8 meters per second squared, 9.83 in this case, divided by the universal gravitational constant. We can look that up. Remember to square the radius, and so we get times 10 to the third meters because it's in kilometers. We end up 5.979 times 10 to the 24th kilograms, which if you go on Google and look it up, I may have looked it up recently. Let's see if I go back. Go back. Mass of the that's mass of the sun. I'm looking something up. 5.972 times 10 to the 24th. 5.979, close enough, times 10 to the 24th. So this is identical to the best value to 3 significant digits. So the 9 and the 2 are a little bit off. But that's close enough. That's actually pretty good. This little tiny bit of information, and you can figure out the mass of the sun. Think about that. Okay. This is 34 on your own. Calculate the acceleration due to gravity at Earth due to the moon. Okay, so now the acceleration due to gravity is now due to the mass of the moon. We're using this equation up here again, but it's not due to the mass of the Earth. It's due to the mass of the moon. So what we do here is two things. We stick in the mass of the moon here, okay, and we stick in the distance from the Earth to the moon here. Those are things you look up. So this should be the mass of the moon, 7.35 times 10 to the 22. If I come back over here, mass of the moon. $7.347 times 10 to the 22. That's the same thing. See, we got it right there. Okay. And then the distance between the Earth and the moon. That's something else you can Google. Distance from, there it is right there. Distance from Earth to moon. They'll probably give it to me in miles though. So go in meters. In kilometers is good enough. 384,400. So that'd be 384,400 times 10 to the third. And we've got here 384,000 times 10 to the 8th. Same thing. 3.84 times 10 to the 8th. You just add 3 zeros and you count over. See if you do this. So you add 3 zeros and you go 1, 2, 3, 4, 5, 6, 7, 8. 3.84 times 10 to the 8th meters. Same thing. So we get the acceleration due to gravity at the surface of the Earth due to the moon, not due to the Earth, is only 3.33 times 10 to the minus 5 meters per second squared. Way less than what it is due to the Earth, so we don't even notice it. Due to the Earth, obviously, it's 9.8 times. That's 9.8 meters per second squared. Here we're talking 3.84 times 10 to the 8th. I'm sorry, 3.33 times 10 to the minus 5. Okay, B. Calculate the acceleration due to gravity at Earth due to the sun. All right, so now what we do is we stick in the mass of the sun. We just saw that a little bit ago. Well, it's not, you can look it up. It's going to be 1.99 times 10 to the 30th kilograms, and then the distance between the Earth and the sun. So now this is distance from Earth to sun. Okay, so remember when you're trying to find the acceleration due to gravity due to the moon at the surface of the Earth, you got to use the mass of the moon and the distance the moon is away from the Earth. When you're trying to find the acceleration due to gravity because of the sun on the surface of the Earth, you use the mass of the sun and the distance the Earth is from the sun. Okay, and then we get 5.93 times 10 to the minus third. So now what we do for part C, take the ratio of the moon's acceleration to the sun and comment on why the tides are predominantly due to the moon in spite of this number. See, if you take, this is the acceleration due to the sun. Acceleration due to gravity, surface of the Earth due to the sun. Here's the moon. The sun is like 178 times bigger, okay? But why is that? Okay, we had that way at the end here. Someplace here. See, here's the thing. The sun's impact is always the same, okay? It's where the moon is that causes the differences. So here we have a combination of the two. So right now you've got a big force on the part of the ocean that's closest to the moon and the sun. A smaller force on the Earth. So it's like this part of the ocean got pulled towards them. And then over here, this part of the ocean got left behind. Now if the moon's up here, boom, we don't see any impact because the moon's kind of having the same gravitational force everywhere. Okay, so there's little impact. The sun's impact is the same, but the moon up here, the impact is going to be pretty much spread out equally everywhere. Then the moon gets over here. Okay, now what happens is this part's getting pulled this way by the sun. This part is getting pulled this way by the moon. So you'd think maybe this part probably doesn't come out as far as this part does. But still, there is a bulge. Okay, and the Earth is spinning around this ocean. And so that's what's causing the high tides. All right, so that's, and then let's see what is the answer they give here. The moon has greater effect than the tide since it is the difference in the pull of the body on the near side of the Earth versus the far side. The Earth's diameter is much more significant at lunar distances than at solar distances. Okay, this is chapter 7. I'm pooped. So I'll tell you what. We'll probably either do chapter 7 in class, or maybe I'll make another. I probably will do them in class. I'm pooped right now. So what I'm going to do is say goodnight. It's 8:11. I don't know how long this went. And I'll talk to you later.